So I'm here to talk about one of my hobby projects, which is Udebs game analysis. It's I don't know how useful it is, but it's super fun to make and play around with, so that's what I'm sharing with you. So there's a GitHub link, the whole project's up there, and all the graphics you'll be seeing is all done through Pygame, which is sort of a Python graphics engine. So the beginning. Udebs started in 2011 as an excuse to learn Python. While working on my master's dissertation, working on master's, I need a break from it. Inspired by my love of Final Fantasy, I wanted to make an RPG duel in Python. I wanted to have like a bunch of zombies on one side, a bunch of like rangers and people on the other side. I wanted to select moves from a menu and cast things. And so what came out of that is, and there's actually music to go around with it. My little brother made the music. This guy right here, so you can actually move. And if you hit an eye, so it's, let's see here, you're gonna go magic against this guy, who's dead. Anyways, so I'm not just gonna play it through, but, so this was the original project. Nothing, my little brother made the music, I was super proud of it, but then something happened. And I'm like, I wanna change the attack power a little bit. Oh, I want to add more moves or add less moves, and I got tired of digging through piles and piles and piles of code trying to find that one variable that changes the attack power from one to the other. And so I started moving everything to config files. And once I got everything to config files, I'm like, okay, well, how do I read from those config files and do this? And then eventually an entire game engine comes, not a game engine, but an engine comes out of it. But eventually my interest moves away from just playing the games to understanding them, to analyzing them, to learning to win. So another hobby I do is I play a lot of competitive games. So I like backgammon. I played Street Fighter competitively, that's a video game, for 4 years. I play card games, and I play a lot of really, really dumb children's games because I worked at summer camps. And what is a better way of learning how to win at stupid children's games? Quick thing about what is game analysis. Game means a hell of a lot of different things for a hell of a lot of different people. I have met people who thought game analysis meant the same thing that literary analysis meant, because games have stories in them. There's game journalism and game this. In a mathematical sense, you have game theory, which is more decision theory, and then and all that type of stuff. So what I am going for is, for the sake of this presentation, a game is the universe that resides within a set of mathematically defined rules. We'll go with that. Calvin Ball is not a game under this definition. Although, if we remove the mathematically defined, maybe it would. And for me, the game analysis is the act of exploring the possible states a game can take in order to find strategically optimal positions, answer questions, or make cool graphics. Because yes, games are also about making cool graphics. So Udebs started as an RPG battle duel and became a system for me to learn about the various games I like playing, whether it be Chopsticks or Tic-Tac-Toe or Connect 4 or a lot of other really cool things. I even used it to find the optimal combos in Street Fighter. We'll just start with the Udebs state model. Really, really simple. There's one object. Python creates a single object, and that represents the entire state of the game. The object is based off the config, which I'll show you in a bit, and it has a couple methods. One of them is do an action. So you give it an action, you give it the object doing the action, you give it the object receiving the action, and you give it the name of the action itself. And then Udebs itself will then decide if the action is legal, and if the action is legal, it'll update itself into the new state after the action is done. If the action is illegal, it will return false and do nothing. So I actually want to show an example of that. Oops, not that one. I have way too many windows open. This one. Okay. So very, very simply, the state objects, I have this little k. K is allowed to move 2 squares on this hex board. If you notice on the right side here, I should probably blow that up. Yeah, I'm going to do that we did before and try to increase the font. If I can. There we go. That's where I was before.
I think you can just do a zoom in, zoom out on the.
Just like scroll.
Maybe a plus.
I think it's Control Shift plus. Control Shift. There we go.
Yay.
There we go. Okay, so I have a running log on all the stuff that operates. So in the thing right there, it tells you literally everything the game is doing. So when the game being this thing right here, opened up, it initialized itself. It initialized a script called init. It's init. Then initialized another script called earthquake. It recruited earthquake, and I don't know why I called it that, but it recruited these mountains into a random location. In fact, this is a really terrible place for mountains because it does not demonstrate when I want it. There we go, that's a better place. And then, so my character is allowed to move maximum of 2 squares, as defined by the green things. If I click inside the square, it'll update, and so as you can see, token uses travel and moves to the map. If I move into a place that's illegal, if I click on a place that's illegal, it will attempt to use click, and then will attempt to use travel, and then it will fail because I have created this condition. So the distance it's traveling has to be less than or equal to the stat of the card, which is the action, and then it doesn't do updates. And then once we get into here, you'll notice I can't move across the mountains, and I can't move across the mountains or in the mountains. So that's a simple definition. How is that defined? Well, this was the fun part of this whole project, and I eventually had to, I probably should have just, but I was experimenting at the time, so I eventually made config files. It's funny to keep it in XML because I was learning that at the time in JSON. Eventually, as this got more and more sophisticated, things got a little bit more ridiculous. So Udebs defines an object as just a thing with 2 attributes, effect and require. Require is the conditions which must be true for the action to proceed. Effect is how the state changes. So in this verse, I have a click.
Can you zoom in a little bit?
Yes, this one I think I can just do that. Okay, so I have an init script, which has 2 effects. It's going to cast an earthquake, which spawns mountains, and it's going to move the token into 0, 0. I have a metric here, which would require, and which says that in order for it to be a legal move, the square must be empty. Ignore that. Here is my travel. So what require, I need to be able to move maximum of 2 pieces, so that's equal to my caster stat act, and then the effect is to move it there. And then the earthquake is, it just rolls a dice and puts a whole bunch of mountains there. And that is the entire thing. And Udebs reads this and generates that entire world from it. Okay. And let's actually, might as well look at the actual script for Hex, just to show how this is used. Almost all of this is DrawScript. The only actual Python stuff is we initiate the game right there. I have a while true, and on the mouse button down, it does a bunch of checking because it's almost all DrawScripts, and then finally it actually casts main move dot control move token XY click. So it generates the entire game through effectively 3 lines of code and some XML. I wanted to, let's talk about this a little bit more directly. Here's a rock, paper, scissors script. Import Udebs, create the rock, paper, scissors, and then I'm going to have the computer player play paper and the user play rock. And what's going to happen is both moves get registered. Computer uses paper on user, and user loses a life. User uses rock on computer, nothing happens because rock does nothing to paper. And then user has 4 lives and computer has 5 left. And we can run that again. And you'll notice the user is now down to 3 because he tried to play the same thing twice. Okay, so what can we do with this? So originally, the first thing I did was just to play the game, you know, I had to play stuff. But once you have one object that represents an entire game state, you're like, can I generate all the game states in a meaningful way? Can I do something with that? Because the system will protect itself against going to a game, so I don't actually have to generate much code to dig into it. So I'm just going to give you the basics of tree search. Tree search is the idea is we're searching through a tree, and so the tree means the root state. So when I created Udebs, I created a root state, and every time an action succeeds, it creates a new state. So a different version of that object. And so effectively, we're searching all the possible states for something. You know, depending on what you're doing, in a mathematical sense, you're always looking for some winning condition. In my sense, I'm maybe not looking for winning conditions. Maybe you're playing a game that always ties. And so you're looking for a cool state that maybe makes a nice graph, or that a small child is unlikely to have memorized. Because once again, winning against small children is key. And so I was going to go through an example game. I need a volunteer from the audience. You, okay, come on. I'm going to teach you a game that I learned at summer camp that all the 10-year-olds are playing. It's called, I'm going to find a spot where everyone can see us. Okay, put out your hands like this. Okay, we both have one finger on our hands. Okay?
Is it chopsticks?
It is chopsticks, yes.
Okay.
All right, we both have one finger on our hand. We take turns tapping fingers back and forth. I tap 1 against one, he now has 2 on his hands. It is his turn.
Sorry.
I have 3 on my hand. We have 3 turns. I can tap this one, now he has 5 on his hands, and his hand closes. His hand is out. His turn. Depends on how you, yeah.
I go with
You go that one? Yeah, I'm gonna go that one.
And you...
No, you have to split on, the game is truly boring if you can split whenever. Anyways, and then he's out of hands, and so I win. It's a simple game like that. Yeah, if you can split on 3, the game is truly infinite, and there's no winning state ever. Like literally, you can never win, the game never ends, you can play randomly, and as long as someone splits when their hand's out, it never ends. So that's the game. I learned that at summer camp, and after 2 months of playing this game, because I'm kind of got to be playing and it's the kids playing it, I have realized that this game actually has quite a sophisticated structure to it. And I need to know all of it, so that I will never lose a game ever again. So rules are, I went through this. Yeah, rules, so every rule is broken up into an entity. 2 main properties, an effect and a require. So the example of an effect is a player must have at least 1 finger to initiate an action. If you do not have a finger, that hand cannot initiate an action. And the effect is target receive fingers equal to the caster's finger stat. So let's look at the actual XML of that. Let's go to chopsticks. Got it right here. Okay, so first off, we're going to create an initialization script, which has, I'm going to give 2 actions to player 1 and 1 action to player 2. It's just a trick I can do to make sure they iterate back and forth. So whenever someone makes an action, their action goes to 0, and I increment both actions. So in this case, only player 1 can move, player 2 cannot move. If player 2 tried to move, this script would reject it. I have just a print script in there because they're useful. I define 2 objects, player 1, and right at the top here, I have to define my actual attributes on it. So I'm going to define an action and a number of fingers. So this is just a number that's held with the object. So down here, I'm going to create a player 1, and then I'm going to give him a left hand, and I'm going to give him a right hand. And both left hand and right hand have one finger, as defined right here. Okay, player 2, and player 2 gets a left hand and a right hand. So then I'm going to get a unit, I don't even remember what that one does. But anyways, here's attack. Okay, so required the target's fingers have to be greater than 0, and the player can't attack itself. And the effect is target fingers gains the caster's number of fingers, and the target action is it's going to attempt to close. So it's going to do a close check. And finally, the split. That's what he was trying to do. If you have an even number of fingers in one hand, you can split them to the other hand. So if you have 4 fingers, split 2. 2 fingers, split 1. He tried to split on 3. And you can split that. There's literally nothing you can ever do. And that's basically the entirety of the thing. Okay? So, and I think I talked about here. So in defining the tree search, I needed to give it a couple of things. First off, a heuristic that approximates all legal moves given a state. Technically, I could go through all legal moves, but like that would, you're gonna be attempting to open up a lot more nodes that are actually there. So just giving it as a simple heuristic that says, here are the potential moves you could be making, speeds things up dramatically. A function that returns a value of the state if it is a leaf and none otherwise. So if this is the end of the game, you need a function to check for it being the end of the game. And an immutable representation of states that accounts for symmetries in this game. So, and it's kind of a name of the game. Just so it doesn't, there's a lot of symmetric positions in this game. I think there's like 800 something states. But once you account for symmetries, like 2 on your left hand and 1 on your right hand is the same as 2 on your right hand and 1 on your left hand. So I have, just for lookup sakes, an immutable representation of the state itself. And then, here we go. Yes, let's go to this guy right here. Okay, so that's it. I have this thing called pstate, which just returns a string. That is just the number of hands that people have open. I have a heuristic for legal moves. I have, it's just checking if player one's hands added together equals 0, then it's a player 2 win, and likewise it's a player 1 win. Otherwise, return none. We don't know who's won yet. And then I have a couple other functions down here, and so this is actually my tree search. So I'm just going to, for substate and self.states, check if the result is equal to none. Add to my storage so I don't repeat states, because this is an infinite loop. And if it's not completed, just redo the graph. And that's it. So I'm going to check the state here. Then I'm just going to iterate over all my storage. So once I put all the states that I've done in storage, I'm just going to pull them up, create the source target CSV that, and I don't know if anyone's used Gephi, but that's what I'm going to be visualizing this in, and then print it out. And what do you get? And then you throw in some recursive iteration and Gephi magic, and you get this little guy. So this isn't all the states in Hex. In Chopsticks, I've actually thrown out all the winning states. So any state where someone can actually win has been removed. And so this is all the states that just cycle through each other. And so how can we use this to discuss a strategy for Chopsticks? Well, because it's a game of mistakes, the game will go on forever until someone makes a mistake and then loses. You put them through difficult situations where it's very easy to make a mistake. And oh look, there happens to be a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then you can send them right back into the same path. 15 consecutive states in which there is only one action they can possibly make to get out alive. Any other action will result in them losing. Those 10-year-olds don't know what's going to hit them. So I've also done similar things with, that's the wrong project. Right here. Udebs. So I've also done some similar stuff with tic-tac-toe. Right here. So this is all games is tic-tac-toe and how it runs. Similar thing, just not as pretty of a visualization. Someone can play in. So my argument is, so what's a strong play in tic-tac-toe? Corner, middle. Well, if we play corner, this is the entire game state. A 10-year-old can easily memorize that to figure out and never lose. Middle, even smaller game state. 10-year-old can very easily memorize that thing. Let's play the edge. Let's play the one that they never want to play. Oh look, it's massive. They don't know what's going to hit them. Yeah, and so there's a couple just other random demos that I have, just things that I've tried, so Python. So I was playing around with simulations and I just wanted to put up some basic river flowing things. So in the top left-hand corner is a source. I'm adding water to there every tick, and it just flows out to the ones wherever it wants to. And there's I did some hardness and some random things there just to make it more exciting. Otherwise, it would just flow out from where it's going. So this will just go on forever. It's cool. And then to really test this thing, I'm doing a chess engine. It doesn't play chess, but it can calculate legal states in chess. And then let's put, I don't know, I need someone else to put the king into check. I really need to turn off forcing turn order. All right, well, the king can't move into check, so that's the one I wanted to show is if it will prevent moves if the king is in check.
So hand capture.
Yeah, we'll go there. So now if I click on any of the black pieces, none of them are legal unless I'm moving the king, or I can move the queen, or I can move this bishop. So it takes into that count. And the rules for this one is quite large, because apparently chess has a lot of weird rules to it. This one right here. So we can recruit, as that goes on for a little bit. But it's really cool because, let's say I want to change the knight travel. It travels 4 squares. And there you go. Now the knight travels 4 squares instead of 3.
Yeah, that's pretty cool.
So, okay, back to here. I'm, by the way, super proud of this graph. Like, I wish I could say I did that all in Python, but no, I did the actual graph in Gephi. So, was it worth it? Like, literally 8 years I've been working on this thing. So I thought it would be simple to represent rules, but quickly realized that XML config files are essentially their own programming language at this point. So I don't know if it'd really be practical for someone else who's not me to use it, but it is what it is. System is way too slow for any large-scale tree search, chess, hex, Go, etc. Will always lose in performance to software dedicated to that specific game. That's just the way things are. Tree search is hard to generalize. There's still enough code that needs to be written that I can't really call it user-friendly. I thought I could just generate the tree as a function, but the fact is depending on what you want to get out of your program, if it's just a matter of finding an optimal solution, then maybe alpha beta search, but if you're actually trying to make a visualization, then prune search, like you'll be pruning it in your own way. Like for instance, I'm pruning winning states instead of all that stuff. And anyways, I had a ton of fun doing it in the process, and it was just a lot of fun doing it. So it's all Python. Yeah, that's really all I've got. Unless someone wants to like actually dig into the code of the actual like library. I don't know. Okay, well, I'll call it there, and if someone asks me a question about digging into the code, I'll do that. Yeah. Questions?
So in the big sort of graph you had there,
Yeah.
essentially you have a graphical proof of a winning strategy.
The problem is yes, but mathematically there is no winning strategy for this game. Like in perfect play, it will cycle indefinitely, and here's a graphical proof of it. From starting position, you can always get back to the starting position. In sub-perfect play, then a winning strategy, like if you're having just lower than perfect play, a winning strategy would be to maximize your opponent's opportunity to make a mistake. It's kind of how I prefer sub-perfect play. And in a lot of these games, sub-perfect play is a little more interesting than perfect play because it doesn't take much of a library to prove that this game is infinite. Like it is kind of mathematically trivial to show that there is no winning solution. Let's just move on. I think it's a lot more interesting saying, okay, it's sub-perfect play. People can make mistakes. It might be rare, but let's try and optimize our opponent's ability to make mistakes. That's kind of how I treat tic-tac-toe as well. Like it's mathematically trivial to show that tic-tac-toe is a tie game. Nobody ever wins. But you start digging deep into it in actual real play, it's actually hard to memorize the entire state tree of tic-tac-toe. It's actually really easy to win at tic-tac-toe because a lot of people say, oh, of course it's a tie, and they just go into it assuming it's a tie, and then bam, you've won. Because you know some deep things in that edge case that they didn't know about. So that's what I say. So the math is a bit weird on that.
So, but could you use this to do graphical proofs for games that we do not necessarily know the full mathematical properties of?
So it depends on how big the state space is. As I said, it still uses tree search, and if you can run a tree search algorithm, and for a proof like this, you pretty much have to do an exhaustive tree search. In fact, this one I did have to do an exhaustive tree search because when the thing recurses in on itself, there's no way of knowing the state of a node until you know the entire rest of the graph. If it's not feasible to do an entire tree of the game, then I don't think I could use this to prove something. You can prove substates of it. You can prove positions. If we put restrictions on it. That's the one thing with tic-tac-toe is to bring it down, I had to make some assumptions on the player. It's actually not, what I showed you is not all of the state trees. It's actually assuming that someone's always smart enough to block if the person's going to win the next turn. The state tree gets a whole lot bigger if people are like, oh, you have 2 in a row, I'm going to play over here. So you still have to reduce the state intelligently.
Yeah.
And I do like the idea, and I do like the graphical representations, because even if mathematically it's an uninteresting game, sometimes people still play it.
Yeah.
Checkers is a solved game, but people still play it, and there's still structure in there. So just because we know how to win at checkers does not necessarily mean that's all that's left to explore in there. Any other questions?
So I was interested in the XML config format you've got. You kind of got half of a domain-specific language there. Have you considered extending it to making it, maybe not XML syntax, but a specific syntax just for?
Kind of, yes. The syntax there was heavily inspired by Lisp, actually.
Yeah.
And I did some like syntactical stuff just because like, I don't know about you guys, but like there get too many brackets in there, my brain just starts to work. So like I did some things like, so the brackets here, I think, dude, I have an examples in here. Oh yeah, I put dots in here.
Yeah.
So you can dot things together and it's like putting brackets around it, but I don't know, just for me it makes it easier to read instead of just having this brackets upon brackets upon brackets. But yeah, it's very much designed. The syntax is simply there's a bunch of keywords in there and it's searching for keywords. And if it finds a keyword, it calls that function with the arguments that are next to it. Sometimes I put the argument around it, but I don't know. There was no real good ordering for a lot of this stuff. In general, I tried to put like, I don't know, this name.c. Oh no, this is chess. Yeah, so in general, I tried to put like the person doing the action before the move and then the person getting acted on after, but that very quickly realized I'm like, honestly, this is just, it's just a function of arguments, like the syntax. So I'm not entirely certain what I'm gonna do with it. It is kind of its domain-specific language, and that's what actually makes it very difficult. Yeah, I can't really, it's hard to document that, but, so yeah, I've thought about extending it, but like, why? Like, like I unfortunately, nobody is, like, it's been up in GitHub for 8 years now, and my most popular repository is a Wark extractor I wrote for, based on the Internet Archive. So, I don't know, I like it, but whether XML is the best language for it, I don't know. Yeah.
Do you handle probabilistic stuff, so like dice?
Yeah, so I literally have a call in here called, let's go back to the hex stuff.
Dice, that's it.
I think I have a dice 7 in hex.
Yeah.
And basically that is basically says roll a 7-sided dice. It's a weird sided dice, but it does. And I have played around with this push luck thing. So there's a card game that I got, which is just you draw a card, you get points, or you get a skull and crossbones. And the question is what's the expected value every time you draw a card? This is one I didn't show off because the answer was draw a card when you have 2 skulls. If you have less than 2 skulls, then stop when you have 2. After serious analysis, I'm like, well, the obvious strategy is still the best strategy. Unless, of course, you have no points, in which case. But yeah, so this thing will actually run through the states similar to a Markov chain and just calculate probabilities all the way up to the stack. So it calculates exact probabilities based on Markov. But this demo is not exciting. Yeah.
Could you add costly moves?
Art?
Costly moves.
So generally how cost is associated is it's a stat in the game. So so let's say I'm casting a fireball and I need 6 mana to do it. What I would do is I would hold my mana as a stat or a state in the game. Let's say I have 12, and on the require I'd say to cast this move you must have greater than or equal to 7 mana, and as part of the effect of the move I would say player mana minus equal 4.
Yeah.
And then that's how you can do it.
Right.
The game also allows for, let's go into the actual life, because I showed that one at the beginning. Let's go life here. So how life works is every time something is resurrected, so the require is the stat life has to be 0, and what it does is it changes the life counter to 0, and then it bumps up all its neighbors by 1. And actually I have it on a delay of 0, which just means do this at the end. Because if you bump up all the ones by 1 and you haven't checked the next one yet, then you're going to do it out. So I just put a delay here that simply says, because there's an internal stack on the order that things are done, so you can actually delay things, do an action, post another action to it, which gets delayed about a couple turns, and then, and this is one of the use cases for it. I want to turn it on, but I don't want to up its neighbor by 1 until I check the neighbor. And then if I actually go to, let's see, XML, let me go RPG XML. Oh, this thing is a nightmare. I wrote this one really early, so there's a lot of, but like for instance, magic missiles effect, change target HP, and description. And yeah, so MP cost is this, so I'm holding an MP cost as a stat on the object. So,
What's the most difficult one you've made?
chess.
That's
Checking for check is the most difficult thing I've ever had to do. I had to implement a whole, what you gotta do to check for check is you have to force the move, you have to copy the state, force the move to happen, and then check if the king is in check. That's the best way I found to do it.
Did you try that for Go?
What?
Did you try that for Go?
You would blow my system up. the states, I say simple games, that like we'd be 2 moves into the game and we would have a memory error. That game is, and chess is the same way. So that's why I mentioned most of the games that you can actually analyze fully in this, a dedicated tree search algorithm with maybe doing like a robust alpha beta or maybe a proof search or something like that can solve in 10,000 times faster than this thing can. The difference is this thing you can play around with. Those ones you're probably going to hard code the rules in something like C or C++ to make it as fast as humanly possible because you've got to do what, millions of states a second.
The approach people have been using for systems playing Go is completely the opposite of it. They use neural networks to recognize states.
Even with the most optimized tree state algorithm in the world, you'll never even touch Go.
Because the search space is so huge for Go that
How many opening moves are there? What is it, 32 by 32 or how big is the board? 17 by 17?
Yeah.
So there are 17 times 17 possible opening moves with 17 times 17, it's actually 17 times 17 factorial is I believe the full robust state base, and I guess you can reduce that a little bit with symmetry, but yeah, my little engine is nothing. It's got nothing on that. You'll run out. I don't optimize that. So I focus on simple games because once again, if you're doing a really complicated game, you're going to need dedicated hardware or dedicated software.
Okay, let's thank the speaker again.